So we will go to the sort of the main part of the course, unless you tell me to still remain with some revisions or something else that you want to still know among the topics that we already mentioned or something else. If not, we will begin with some, I will go through the algorithms one by one and then do some error correction and others. So, one of the first algorithms that were given, quantum algorithm, is the Deutsch Jozsa algorithm. Maybe many of you know it already. It's sort of a simple one. I mean, the mathematics is simple. So let's there's a paper by Deutsch in 1985 already, but we will do the version that is by Deutsch and Jozsa in 1992. There is a good discussion of this in Ujjwal's book. Well, Ujjwal has written several books. In one of those books, it is at page 133. I don't know which one, okay? I've written Ujjwal's book.
So by how many you mean, like how many books?
10 maybe, or less than 10, certainly. 5, 6, something, I don't know. So try all page 133s in them. So, so this algorithm concerns this. All of you have seen Sholay, no? So it concerns the main character of Sholay. Who was the main character of Sholay? Any other options? Akur. Thakur. No, the main was the coin. So, remember the coin in Sholay? We try to find whether coin is fair or biased. Yes? So, the coin is represented by a function f. F takes 0 and 1 as input. I'll tell you what 0 and 1 means. The outputs F0 and F1 represent faces of the coin and they are either 0 or 1, yes? So this 0 is at the input, whereas this 0 is at the output, okay? We should not confuse between them. So at the output there are F0 and F1, so these are of course the head and the tail. And but then this can be either head or tail, this can be also head or tail, and then that head and tail we call them again 0. So this is like H and T, yes? If F0 is not equal to F1, the coin is fair. And if F0 equal to F1, the coin is biased.
So the input 0 or 1 means like we are looking at the side 0 and
Yes. You are looking at the top side or looking at the, and you assume that the coin doesn't fall like this. So yes, so this I am not discussing, okay? So that, I mean, the input 0 and 1 has to be given some meaning. Yeah, you call something as towards the Alpha Centauri or something, and you say that that is where you are looking at when the coin falls. So now classically, if you want to find out whether a coin is fair or biased, you must look at both sides of the coin. It is a trivial thing. This is what the mistake that Jay did in Sholay, yes, and not Jay, the other one, Viru. Viru did in Sholay, yes, he didn't look at both the sides. So, so that is a trivial fact. Classically, if you want to find out whether a coin is fair or biased, can you see this? You must look at both sides of the coin. Yes? That is, you must evaluate the function f twice. Yes. Looking at the coin is evaluating the coin, evaluating the value. So you look at the top, look at the bottom. So you evaluate it twice. So first you find something F0 or F1, then you find F1, order unimportant, order is not important, and then you check. like this. If it is, then you say it's biased. If it is not, it is unbiased. Fair. True. Now we will make an assumption.
Sir,
Yes.
when we are checking if the by bias means that it will land both ahead and desk 50% of the time.
So yeah. So this is not the colloquial meaning. That is what is it in the practical case. So we are doing in this 1, 0 at the ends. So it's like terribly biased. Yeah. You're looking at the probabilities, but the only options are that the probability is 1 or 0.
And both faces are the same.
Yeah, both faces are same or different. This is what we are looking at. We are trying. So you can change this problem to make it into the thing that you are trying to say. That will require more algebra. So we are trying to see whether it's at the very end or slightly away. So this will not have any practical implication, because even if it is like infinitesimally away, this will show a difference.
That is good, right?
Pardon?
That is good.
No.
No.
It will hit to the left or right. It will
That's
not-
So
sometimes that's it.
in a realistic situation, somebody wants to cheat you, will of course not make the head and tail the same. Yes, she or he will make it such that maybe 60% of the time it falls head and 40% it falls tail.
In this
And
case,
then by looking at it, you won't realize it.
in one toss you won't,
Oh.
but in this case,
In this case, we are allowed only one toss. This is the thing. So in that case, we will have to do many tosses and change the algorithm. So this is essentially to show that in the quantum case, you can have better algorithm. This is essentially existence proof, so to say. So we will show that in the quantum. I haven't stated the problem. Let me state the problem. So to state the problem, we will make an assumption. So the assumption is that suppose now that the evaluation of f is difficult and it is not possible to calculate it twice. This is actually means well, of course, for the for tossing the coin not, but I mean there are realistic situations where evaluation of a function is costly. Yeah, I mean you will many times if you do some numerics or something, you will many a times land in situations where the very evaluation of the function is actually where you know the function, but to actually run it and find it is costly affair. Also suppose that you can still evaluate it once. Okay. So I'm assuming that it's very difficult. I will calculate it once or not once. This is my condition. Only then the problem survives. Now classically, then you cannot
able to evaluate it once. Is it with respect to time? Like there is a time constraint or?
You can consider it like that. Maybe it takes like, you need the problem in 3 days and the evaluation take 2 days once. So you will take 4 days to get the classical answer. Whereas one evaluation take 2 days. So that is a good point. So of course the question is, can quantum mechanics help? Well, of course it does, otherwise we won't discuss all this, but we will see how it does. And by the way, this is, I mentioned Blachovator's book because in that book, either I may have copied from there or I liked it a lot. It's quite a few years before I made this thing. But this algorithm is there in every standard book, okay, Nielsen Chuang. I don't remember, but I'm assuming that it is there in all books, wherever, any standard book, the Kitaev book or the Nielsen Chuang. Is it there in Breskill? I don't remember. It must be there. It's a very standard one. You always begin with this. It's very simple mathematics. So we will define the quantum algorithm. So for that we will need some notations. We'll define those notations now. Consider an operator UF that acts as so this is my UF, it takes in 2 inputs, call them X and Y. And the output gives out X here, so nothing happens to this. And in this one, it gives you Y plus Fx. So this X and Y are 0, X is 0, 1 and Y is also 0, 1. These are the options. So these are qubits. This is addition modulo 2. We define this operation. So take it as a problem. You can do this. It's actually very easy. Show that UF is unitary for all F. Yeah. So you can do it explicitly.